probably been told that to take advantage of compound interest, you should start saving for retirement when you're young. But that is only part of the picture. Abby and Courtney both start saving $300 per month for retirement when they're 25, but they will arrive at radically different outcomes that they've saved from for their retirement by the time they hit age 65. In this video, we're going to follow three people, Abby, Blake, and Courtney, and see how their different investment strategies work out for them in the future. Who will be further ahead, by how much, and why? I'm going to answer all of these questions and then leave you with one important question for you to consider. So be sure to watch to the end for the most complete understanding of compound interest and some of the risks involved. You do not want to be uninformed. So each of Abby, Blake, and Courtney are going to save $300 per month. They're going to save from the age of 25 to 65, so that's 40 years. And the number of compounding periods, the number of times interest is going to be paid by the bank, is 480. It's paid every month. Every time an investment is made, the interest is paid. That is what a simple ordinary annuity means. So we take 40 years, we multiply by those 12 times the interest is paid, we get 480. The total money that they've saved is the 480 times they've saved the money times the $300 that they've put in the account each time for a total of $144,000. So let's consider our three scenarios. Abby is investing in a bank savings account at 0.5% interest. Blake is investing in some low-risk investment, maybe bonds or GICs, at 4% interest. Courtney has a higher risk investment, which means it could fluctuate more, but overall it's going to have an 8% average interest each year that she invests, maybe mutual funds or ETFs or something like that. Now, what we know is that a 0.5% interest rate is not nearly as good as an 8% interest rate. So we assume that that might look a little bit more linear because it's not a ton of interest. 4% might have a little bit more curve, and 8% might have a greater curve in the amount over time. But how great is the difference between those? That's what we're after here and what we really want to understand. So just to convince you that a bank savings account is something maybe about 0.5%, I've taken this off of my own bank. You can see that for $0 to $50,000, they're saying that 0.3% is what they'll pay you in interest, $50,000 to $100,000, 0.5%. And then if you're over 100,000, you can see that increments bigger than that. So let's just assume for the sake of simplicity that it's 0.5%, and that's how I got Abby's number. Now it's important to first understand the rule of 72. It's going to be a guiding principle in the back of our minds as we do these calculations. It says this: if you invest a principal amount of money one time, divide 72 by the interest rate. The answer is the time to double your investment. So let's look at this in terms of the three examples we have. For Abby, we take 72 and we divide by 0.5%. It's going to take 144 years for her to double the amount she invests. This is if she invests all her money at once. And so this is different than the annuity we're calculating, but it's still a good guiding principle. Blake takes a 72 and divides by his 4%. It's going to take him 18 years to double his money, which is not too bad. Courtney, on the other hand, takes 72 divided by 8%, she's going to be 9 years. And so if you can get even a 12% interest rate, which tends to be very, very fluctuating and very, very risky, you could even get it down to 6 years. But you'd have to be comfortable with a lot of volatility. So what I noted already is that there is a difference between what we're looking at and what the situation is here. So our situation is an annuity. It's investing a small amount of money at regular intervals, $300 per month. The rule of 72 applies to a one-time investment. So in other words, if any of these people put, like let's say $10,000 once, then we could use the rule of 72 to say how long it would take to become $20,000, for example. Okay, so it's not going to apply exactly because different amounts are put in at different times, which means that has different doubling times for each of those specific $300 amounts that's invested. If this is helpful so far, please like and subscribe and keep watching here as we look at each scenario. So calculating each scenario, Abby, 0.5%, she goes ahead and calculates this. Her future value is equal to R. R is the amount she's investing. So that's the $300 a month. And the 1 plus I to the N, I is your percent as a decimal. So you take your 0.5%, you divide by 100 to turn it to a decimal, but then you have to divide it by the number of compounding periods per year. There's 12 compounding periods per year, so we divide by 12. And N is the total number of compounding periods over the entire investment. The investment is for 40 years, but there's 12 compounding periods per year, So we need to multiply that 40 by 12, and n is 480. So we go ahead and we sub those numbers into the future value equation, and what we get if we calculate that is we get $159,373.35. So if you keep in mind, we had $144,000 invested, so that means she's made somewhere in the range of $15,000 or $16,000. Not bad, but not nearly as good as Blake. Blake has invested 4%. The R value is 300 as it was before. The N value is 480 again, but the I value for Blake, it's a 0.04. 4% as a decimal is 0.04. And then we divide that by 12. So his I value is much greater than Abby's. And so we sub those values in and we calculate it, and we get $354,588.40. Much, much more than Abby. But Courtney was even smarter. She was also willing to take a little more risk on, a little more fluctuation in her investments. She invested, again, $300 a month, so R and N, 480 times she's invested this. Those are the same. And then I is 0.08, 8% as a decimal, divided by 12, and so it's 0.06 repeated. And so if you sub those in, what Courtney got is over $1 million. And that is a significant difference. And so if we actually look at these graphs that I showed you earlier on, you can see that the curves have very different values on the y-axis. So they're 0.5, 4%, and 8%. We're looking at the amount versus time of each of those graphs. And if we looked at them all on one graph, we would see the following. You can see that Courtney's is the top line, the middle line is Blake's, and the bottom line is Abby's. Very, very different amounts that they arrive at. So as we compare the scenarios, each of these people has invested $144,000. The situation for Abby is that she had a 0.5% interest rate. She invested $144,000. Her final amount was $159,373, giving her $15,000 interest, or 1.11 times her money. Blake had a final amount of $354,588, giving him an interest earned of about $210,000 to $211,000, which is 2.46 times the money that he invested. Courtney has an 8% interest rate, and she arrived at a final amount of over $1 million, giving her an interest earned of over $900,000, and she has 7.27 times the amount of money that she invested that she arrived at retirement. Now let's suppose that you are not concerned about those interest rates, and you say, well, I'll just save more in order to get more for retirement. Well, how much will you have to save every month from the age of 25 to 65 if you wanted to save to $1 million at these different interest rates? Let's look at it from that perspective now. So from Abby's perspective, if she wanted to save, we're going to take that future value equation and we're going to rearrange to figure out what her regular payment would have to be every month. I've multiplied both sides by I, and I've divided both sides by the square brackets, 1 plus I to the power of n minus 1. So future value times I divided by everything in the square brackets. And so now we go ahead and we substitute a future value of $1 million in. The I and the n are just the same thing they were before when we did this calculation. And when we sub those things in and we solve that, we end up with a value of $1,882.37 per month. That's a lot of money to save every month to reach $1 million. Well, maybe Blake, maybe he's not in as bad of a situation. Definitely not as bad of a situation, but let's see how much he has to save to get $1 million. So the I and the N value are the same as they were previously for Blake. The future value again is $1 million. And so we sub those into the equation to figure out what the regular payment would have to be. And we get $846.05 per month. That's still a lot of money to save to get that $1 million in 40 years. Now we look at this last situation, and that's Courtney. And we have all the same numbers as before. The I and the N value are the same as they were previously. Again, though, we're saving to a future value of $1 million, and we're subbing them into the equation rearranged for the regular payment, and we get a value of $286.45. That is drastically different. In fact, if you compare Courtney's to Abby's, you can see that Abby has to save 6.5 times more every month just to get the same amount of money, $1 million, at retirement. Now, there's another thing to consider that many people miss out on here as well, and that is that inflation causes your value of your money over time to become less. And so if you talk to a financial planner, and you should definitely do that in these situations, they'll tell you that $1 million today is not nearly as much as $1 million 40 years from now. And so you'll have to account for that in your savings as well. And so, in fact, Abby not only has saved a whole bunch of money, or has to save a very, very large amount of money to get to the $1 million, but that 0.5% that she earns on what she's invested, inflation is generally higher than that. So she actually loses money over time because it has not grown as fast as inflation has. So very, very unwise decision on Abby's part. Wise decision if she's doing a short-term investment, unwise if she's doing a long-term investment like saving for her retirement. So let's consider some takeaways. First off, I want an important warning. A higher interest rate comes with more risk. Talk to your financial advisor to discuss what risk tolerances are best for you, your situations, and time frames. As I noted, you don't want to take a big risk if you're in a short time frame. So here's the first takeaway. Compound interest is paid on the principal and interest. So the higher the interest rate, the faster your money will excel. Speak to a financial advisor to help find investments that are better than a bank savings account for longer term investments. You should absolutely do that. But also diversify your investments. Do not put all of your money in one investment, but many different investments. Some investments can be very volatile at different times, and you don't want to lose all your money all at once because it's all in one type of investment. So what should you consider? How are you, or how do you plan to use your compound interest to your advantage in saving for future things like your retirement? That's the big takeaway from this video. How can you be wise with that? And how can you use compound interest, just like Courtney did, to save for things? If you're saving for something more short term, you can still find something that's much better than a 0.5% bank account. If you found this video helpful, please consider subscribing and hitting the bell notification to see my future videos. For more on future value annuities, like saving for retirement, see the video on the left. For more on present value annuities, like paying off a mortgage or paying university off from money that you've saved up, see the video on the right. Thanks so much for watching. May you be wise as you save for the future.